The photograph in Figure 5 fixates the process of reconstruction of a strong hologram. The data are given in Figure 4b, d. One can clearly see the energy propagation channel, orientated perpendicularly to the front and rear sample faces, i.e., directed along the isophase surfaces of the hologram. The energy distributions in radiation beams on the hologram entrance and exit faces, Figure 4c, d, are processed experimental results. Parameters of beams on the hologram entrance face correspond to those of reconstructing beams used in the experiment, while the beam intensity distribution on the exit hologram face is calculated with account of the hologram phase modulation. The phase modulation for each hologram was found experimentally by the value and the shape of the angular selectivity contour. The calculation for Bragg diffraction of Gaussian beams by periodically modulated media used the technique, published in works, Chu and Tamir, 1976. The calculated results for the beam intensity distribution on the exit hologram face are in qualitative agreement with the picture of beam diffraction, observed in the experiment. As noted, the terms weak hologram and strong hologram for a transmission volume phase hologram bear no relation to the value, but are defined by the value of phase modulation amplitude phi1. The value for holograms in the experiment, which was attained under Bragg conditions in the two cases, is less than 50% for both the weak and the strong holograms. Despite the close values of the appearance of the spatial intensity distribution for either of the two interacting beams, diffracted and zero-order ones, on the hologram exit face differs markedly. As seen from the data of Figure 4a, intensity distribution of diffracted and zero-order beams on the exit face of a weak hologram 9 mm thick exhibits two peaks that are spaced apart and correspond to the diffracted beam and zero-order diffraction beam, transmitted one. Here, the diffracted beam is appreciably broadened with respect to the incident one and exits the hologram strictly opposite to the incident one, i.e., the diffracted beam energy propagates along antinodes of a hologram grating, which is schematically illustrated in Figure 4a. The zero-order diffraction beam propagates practically in the direction prescribed by ray optics. On the exit surface of a strong hologram, however, the diffracted beam and zero-order diffraction beam are spatially aligned with each other. The intensity distribution in zero-order and diffracted beams is practically no different from that in the reconstructing radiation beam. The spatial position of the beam specifies the direction of isophase surfaces, along which the radiation propagates. The conditions for running the experiment to observe the energy channelizing effect in reconstruction of a hologram grating 9 mm thick. Table 4 shows hologram grating parameters that enable the observation of the energy channelizing effect. Special notice should be given to the situation observed in the reconstruction of a strong hologram beyond Bragg angle. Figure 5b shows dependences, obtained in non-Bragg reconstruction of the strong hologram, its reconstruction results at Bragg angle having been given in Figure 4d. The deviation from Bragg angle in the case was 0.4 rad, so, after crossing the entrance sample surface, the zero-order beam propagated in the hologram both within the angular selectivity contour delta theta of the hologram, see Figure 2a, and partially outside its limits. The data in Figure 5b demonstrate a very interesting situation. The channelized radiation intensity in the direction of the isophase surfaces is zero as distinct from Bragg conditions of reconstruction, whereas another two radiation propagation channels emerge symmetrically to the right and the left with respect to the Bragg propagation channel. A. Observation of the energy channelizing effect in volume hologram grating 9 mm thick with phase modulation amplitude 10.25 pi, recorded in PTR glass. Incident beam illuminates the sample exit face at a 45-degree angle, beam diameter is 3 mm. B. Processed experimental results for reconstruction of a strong hologram at a deviation from Bragg angle by 0.4 rad, radiation intensity distributions in the reconstructing beam on the hologram entrance surface, solid curves, in zero order, dot line, and diffracted, dash line, beams on the hologram exit face. Hologram parameters are the same as given in Fig 4d and Fig 5a. What is the possible reason behind the emergence of two radiation propagation channels? One can suggest the following general behavior of propagating beams in a volume hologram grating in non-Bragg reconstruction of the strong hologram. The reconstructing radiation beam deviated from Bragg reconstruction condition by value 0.4 mrad, that is less than the half-width of the angular selectivity contour of a hologram at phi 1 equals pi/2, which is in the present experiment about delta theta 3 mrad. Having passed the plane of the first extremum of function eta, phi 1, at pi/2, this so-called first zero-order beam, IO1, can, by virtue of small deviation from Bragg angle, bifurcate and continue partially propagating in the original position, thus forming the second zero-order beam, IO2, that can likewise bifurcate after passing the hologram section pi, and from the third zero-order beam, propagating at the same angle as IO2 symmetrically with respect to IO1. Each of the zero-order beams can form its own propagation channel that should remain, according to theoretical concepts, within the geometrical limits of the cross-sectional area delta pi/2 of the hologram, but may be misaligned with the direction of the radiation propagation under Bragg reconstruction conditions. Thus, the present experiment has realized the scenario of bifurcation of radiation propagation channels by way of selection of non-Bragg reconstruction. In addition, intensity distributions of the zero-order and diffracted beams on the hologram exit surface were calculated for the case. The results of intensity distribution calculations are in qualitative agreement with a picture of beam diffraction, observed in the experiment. Theoretically, one can realize the situation with a large number of propagation channels that should theoretically lie within the limits, defined by the conditions of the experiment on observation of the energy channelizing effect, see figure 3.